hopefully good to go.
Okay, should I
just put you, let me just put you. Of course, I figured out how to do this correctly last year, okay.
hit you there?
Yeah, just putting you in nice and large, okay. All right. All right, now I think we're ready. Okay, so just a brief introduction. So Robert Stein is a postdoc at Caltech. He leads a variety of things, but in particular has spent a lot of time doing neutrino counterpart searches, TDEs, other stuff. And so we're really excited to have Robert who will be talking about neutrino searches with ZTF. Maybe I just make you slightly smaller. Yeah, okay. And otherwise, I think you're good to go, Robert.
Okay, thank you very much for the introduction, Michael, and for the opportunity to talk today about neutrinos, a topic I'm most excited about. For those of you who don't know, this title slide here, this is a picture of the IceCube lab, which I will be talking about. This is the world's largest neutrino observatory. It's located at the geographic South Pole. And as a result, you get a lot of nice pictures of the observatory. And in general, I think I'd like to start my talk by taking a step back, way back to the beginning and saying what actually is a neutrino in the first place, because maybe not all of you are aware or very familiar with the concept. And I think most science talks usually start with a photo of somebody who's been dead for 100 years and made an important discovery, and this talk is no different. So this on the left is a picture of Victor Hess. He's the man with the flat cap in the hot air balloon. And Victor Hess was interested in studying radiation over 100 years ago in around 1912. And at that time, it was known that there was this level of radiation that you could measure all over the surface of the Earth. And so he had this idea because at the time it was thought the radiation came from inside the Earth. And so he thought, aha, well, I'll go up in a hot air balloon and I'll measure how the level of radiation changes over time. And the higher I go, the further away I'll be from the Earth. I'll be further away from the source of the radiation, so I'll measure a decrease in count. And so he set out to do this in Austria. He got in his hot air balloon, he made several trips and started measuring the level of radiation. And what he found was that the higher up in the hot air balloon he went, the more radiation he measured. So he ended up finding exactly the opposite effect to the thing he was expecting. And this was initially kind of puzzling, but eventually it was figured out that this was telling us something very important about the universe, because what it meant is that this radiation that he was measuring was not coming from the Earth. Actually, it was coming from the cosmos. And because of that, it was named cosmic rays. So it was discovered that there was a source of radiation out there in the universe that was coming into Earth. And the higher up you went in the atmosphere, the less shielding there was from this radiation, and the more fully you could measure this flux. And so basically, what he figured out was that there is this flux of cosmic rays approaching the Earth, seemingly from all directions. And you might notice on the right here that these are illustrated with red. If anyone's familiar with particle zoo, these are red proton particles. And the reason is that Victor Hess got the Nobel Prize, in fact, for his discovery of cosmic rays, but they're not, in fact, rays at all. So it was, again, a long and distinguished history of people having good guesses that turned out to be wrong. Cosmic rays are actually charged particles, and the radiation that was being measured is not in the form of rays, because at the time people didn't understand the difference. But nowadays, we know that when charged particles collide with the Earth, you can measure a level of ionizing radiation. So that was 100 years ago, and that was the birth of what you might call astronomy with particles. So it was for the first time people trying to study the universe with things other than photons. And we've learned a lot in the last century. So nowadays, when people study cosmic rays, they don't just have a little hot air balloon. Instead, these are truly industrial scale particle detectors. So on the left, I'm showing a picture of the Pierre Auger Observatory that's in South America. And you can see from the scale, it's sort of 70 kilometers by maybe 50 or something. So it's thousands of square kilometers of instrumented surface area in order to detect cosmic rays. And the idea is that you'll have a proton come in, just like the one that I was showing on my previous slide. And in this case, it will collide with the atmosphere and generate this very extensive air shower. So it will lead to production of particles, which are very high energy, which collide with other things, which produce more and more and more particles. And at the end, you get a very extensive number of particles at the bottom. And you can measure this with detectors. And so why would you be building detectors with such large surface areas? And the reason is that actually what we've learned more importantly is that the universe is absolutely full of cosmic rays. So these charged particles, you can see on the plot on the right here, they follow a so-called energy spectrum. So this is in particle physicist units of electron volts. And it starts at 10 to the 9 electron volts. It's logarithmic, and it goes down to 10 to the 21 or something. And you can see that it follows roughly a straight power law with two main features. So it's at lowest energy is mostly coming from, we think, the sun. These charged particles, then at some point you have the so-called knee. You kind of have to squint to see this, but it kind of steepens. And this is where we think that to this point, cosmic rays are coming from the galaxy, and then beyond that, we're not really sure. And instead it steepens, and then eventually you have the so-called ankle at the end, where it kind of flattens again. There's even more tortured analogy features like the second knee or the second ankle. But I think this is kind of the big picture. And I think it's kind of good to take a step back and really understand what this plot is telling you. So particularly if you look at the highest energy, 10 to the 21 electron volts, what that means is that there is a place in the universe where protons or other charged particles can get accelerated to such high energies that an individual nucleus will have the same kinetic energy as a tennis ball being hit by, I don't know, Venus or Serena Williams or one of these very famous tennis players. So it's absolutely an enormous amount of energy to concentrate into a single point. And you can imagine it's actually very difficult to do that. I mean, so humans have no chance of doing this. There's no way we could build something like this. If you think about the biggest particle accelerator we have on Earth, the Large Hadron Collider at CERN, that will get you to around sort of order 10 TeV, so that's 10 to the 13. And you still have 8 orders of magnitude before you get up to the highest energy that nature can provide. And that's actually really exciting. So the thing that we've really learned is that nature is really good at accelerating particles to very high energies. And the basic idea, it's not so different from what you would think of when you think of a terrestrial particle accelerator, like at Fermilab or at CERN. You basically have protons or other sort of nuclei that will approach an astrophysical source, which may have a strong magnetic field, for example. And they basically are accelerated by processes within the magnetic field and are ejected at much higher speed and much higher energy. And so that's the basic idea, that actually cosmic rays are accelerated by astrophysical processes. And it turns out that nature is really good at doing this. And it would be really nice for us to understand some things about the astrophysical sources where this can take place, because as you can maybe imagine, you need really very extreme sort of physical environments in order to enable this kind of behavior. So that brings us to the field of astroparticle physics, where we try and study these so-called cosmic accelerators. And the first thing you think of is, well, why don't you just detect the cosmic rays and look at where they're coming from? But the problem is that cosmic rays, as I said, are charged particles, and charged particles get deflected by magnetic fields. And the universe is just absolutely full of magnetic fields. So what you'll get in the end is something like this red path that you can see illustrated here, that no matter what direction the protons are initially ejected, they will follow this kind of windy, bendy, curvy path. And so by the time they collide with the Earth, even if you could detect a cosmic ray perfectly, and you could reconstruct exactly how that cosmic ray arrived from that direction on the sky, that still wouldn't tell you very much about where the cosmic ray originated from, because of this deflection. If you would just draw a trajectory back from where the cosmic ray collided with Earth, it would not point back to the astrophysical source. But we fortunately live in this era of multi-messenger astronomy. And so what you can do instead is you can consider other messengers which are created at the same time as cosmic rays, which we can maybe use to pin down the answer to this problem instead. So by messengers, I mean any sort of mechanism by which information can be transferred through the universe from an astrophysical source to an observer. So cosmic rays are one messenger. Photons are another messenger. You also have gravitational waves and neutrinos. These are the main four messengers that we use. So to start with maybe the basic one, I think most of the time, if you're an astronomer and you want to measure something, you want to use a photon. So why would you not just use photons directly to find the source of cosmic rays? Well, there are a couple of reasons. The main one is that photons are actually very easily absorbed at high energies. So when you're talking about particles reaching 10 to the 15 electron volts, for example, you can get photons that will be produced at the same energies at the same time. And photons are not charged, so they will travel in straight lines. However, they will scatter off intermediate gas or just the actual cosmic microwave background. There's a lot of different photons in the universe that other photons can scatter off. So when you talk about very high energy gamma ray astronomy, which is what these energies are, you really cannot see very far. It's very difficult to see even beyond our own galaxy. The other thing is that photons can be produced by a number of sources, and it's very difficult to entangle at high energies whether photons are being produced by charged, for example, proton accelerators, or just through other processes, leptonic processes, which are not the ones of interest. Fortunately, there is the other messenger I mentioned, and the main focus of my talk, and this is the high energy neutrino. So neutrinos are pretty much perfect messengers in the sense that they are also electrically neutral, so they travel in straight lines. They only interact weakly via the weak force, which means that they can pass through dust or other matter, even directly through the Earth without much trouble. And that means that they can travel all the way from the source to the Earth where we can detect them, hopefully at a neutrino detector. And in that way, they can carry information about the origin of cosmic rays. Now, the nice thing about neutrinos is that they can only be produced through the interactions of accelerated cosmic rays. So if you have a neutrino source on the sky, you can be pretty sure that's also a cosmic ray source. So in short, maybe it seems easy. All we need to do is build a neutrino telescope, and we'll be able to unravel the mysteries of particle acceleration in the universe. So what would a neutrino telescope actually look like? And actually, so the problem here is that the very things that make neutrinos perfect messengers, namely that they are electrically neutral and they do not interact very much, also make them very difficult to detect because they are electrically neutral and they do not interact very much. So the first thing you need to do is you need to build a detector with an absolutely enormous detector volume, because there are trillions of neutrinos that are streaming by it all the time, and you really just need a very large detector to have a chance of even detecting one or two. And the other thing is that neutrinos, you cannot measure them directly, but occasionally they will collide and interact. And then that's something that you can measure. So I'm showing here the IceCube Neutrino Observatory, which I mentioned before. This is the world's largest neutrino observatory, located at the South Pole. Right on the top of the surface, you can see the IceCube lab. It's very small, so it's maybe difficult to make out, but that's what I showed on my title slide. And so what IceCube is basically at the South Pole, they basically sent a team to go and drill down through the glacier ice, 2.5 kilometers. And so what you do is you lower a string down into this hole. You have PMTs, photon multiplier tubes, basically just photon detectors. You have like a kind of a photon detector and then a bit of a space and another photon detector. So you have photon detectors evenly spaced along the lower 1 kilometer of this string that you lower down into the ice. You let the water refreeze. And so then your string is stuck there. And you do this not just once, but you do this 86 different times to form a kind of grid. And so that's what you can see here. So you have roughly 5,000 different photon sensors. And in total, that gives you an instrumented volume of 1 cubic kilometer, hence the name IceCube. And so for those of you who don't know, 1 cubic kilometer is absolutely gigantic. The little smudge on the plot is supposed to represent the scale of the Eiffel Tower. The Eiffel Tower is big, and IceCube is much, much bigger than the Eiffel Tower. And then the reason that it's built this way is, of course, to give it this enormous detector volume, and also to be built in a transparent medium. And, ice is pretty transparent. It lets light pass through. And that's important because if you're lucky, you'll have one of your neutrinos passing through, maybe directly through the Earth, as I mentioned, and then it will happen to collide with an ice molecule. And if it interacts, it can produce a muon, a daughter muon. And muons are charged particles, unlike neutrinos, which means that they will give off light. And so what you'll see in your detector is a pattern of light following the trajectory of the muon. And so this is what's illustrated here in the plot. It's kind of color-coded by arrival time. So red is early time light, blue is late time light, and green is kind of in the middle. And you can imagine that if you have an algorithm to analyze this pattern of light, you can kind of track what the muon trajectory through the ice was. And so you can see here, it came from the lower left, passed through, and exited kind of in the middle, going upwards. And if you have a deposition of light like this, you can run algorithms. And when you run algorithms, what you find is that you can localize the neutrino tracks to within a few square degrees on the sky. So maybe depending on the energy, 1 or 10 or 20, it varies depending on the topology of the event. But in general, pretty well localized relative to, for example, gravitational wave detection. So this is already pretty useful. And the cool thing is that once you've done this, you've not just detected a particle from space, but you've got an idea of where that particle comes from. So you don't just have a neutrino detector, but you have a neutrino telescope. So you can do astronomy with this. The other thing that's cool is that muons give off light based on the amount of energy that they have. So if you look at this plot again that I showed you, this illustration, the size of the bores represents the amount of light that was measured at each of the individual 5,000 detectors. So if you do this, you can estimate how much energy the muon had. And if you have a higher energy muon, it will appear brighter. And when you sum up the light, the total will be bigger. So that's the basic idea. And this isn't just a theory, but this is actually, for example, the real data that IceCube measures. And you can see this is basically the number of events IceCube measures in a few year period as a function of energy. And on the x-axis, you can see it starts at about 10 to the 2 GeV. So this is 10 to the 11 electron volts. And then 10 to the 3 is 10 to the 12. And it goes up to 10 to the 6 GeV, which is 10 to the 15 electron volts. And this may not look so spectacular to you, but this is actually the most important plot in neutrino astronomy. And the reason it's important is because if you try and analyze the spectrum, what you find is that you cannot fit this with one single source of neutrinos. Instead, when you account for the detector's effective area and so on, what you find is that there are two different types or two different origins of neutrinos that you're measuring. If you just average over the whole sky and sum up by energy, the only way to describe the data is with a red line and a purple line, as you can see here. And in particular, at high energies, there's a deviation from the trend that would be expected from a single source, like the purple line is showing. So what does it mean to say that the neutrino spectrum has two components? Well, I mentioned that what we're trying to do is we're trying to measure astrophysical neutrinos. So you imagine you have a very distant astrophysical neutrino source and it produces cosmic rays, which produce neutrinos, and the neutrinos travel very long distances. This is not to scale, of course. And then eventually the neutrinos from some distant galaxy will arrive at IceCube and be detected. However, if you have a cosmic ray, and the cosmic ray does make it all the way to the Earth, I mentioned the way that cosmic rays are detected on Earth is through these air showers. And one of the things that will get produced in these air showers is also neutrino, daughter neutrinos from the parent cosmic ray. And these neutrinos are neutrinos like the astrophysical ones. They're completely indistinguishable on an event-by-event basis. They can travel also through the Earth, and they will also be detected by IceCube. And so what that means is that actually, when you look at this plot, most of what you're measuring are these atmospheric neutrinos that come from cosmic rays colliding with the atmosphere. And just as the cosmic rays don't tell you very much about their origin because they've been deflected by magnetic fields. If you would detect a daughter neutrino from a cosmic ray collision with the atmosphere, that also wouldn't tell you very much about where that cosmic ray had originated from. So the only thing that we can use to learn about the origin of neutrinos are these astrophysical neutrinos, but they're buried under this very enormous background. And it's actually really difficult to disentangle. You can't do it one neutrino by one neutrino because they're the same particle. Instead, you have to just do a sort of averaging, and you have to use statistics, and you have to try and pick out the interesting, likely astrophysical neutrinos amongst the very enormous atmospheric noise. And this is kind of the whole game of neutrino astronomy. So let me talk to you about these very high energy neutrinos, where you can see that the red line starts to be larger than the purple line, because this is actually the main focus of my talk, and one of the main ways that we do neutrino astronomy is we just only consider the very highest energy neutrinos, which have energies above maybe 100 TeV or 1 PeV, so 10 to the 14 or 15 or 16 electron volts, this kind of range. And so when IceCube detects a neutrino, I mentioned that the muon gives you an indication of what the energy of the parent neutrino was. And if you're lucky, you can then find this automatically. So IceCube has algorithms that run to say, oh, there's a high energy neutrino that's been detected. And when they do that, they then transmit this data immediately via GCN, the GCN network of sort of real-time astronomy information, to allow astronomers all around the globe to say, actually, there was a neutrino and it was detected from this direction in the sky, and to encourage people to point their telescopes and have a look and see if maybe you can identify a possible neutrino counterpart with that information. So that brings me back to now maybe the astronomy component of this talk. So how can you use a telescope like ZTF to search for neutrino sources? The first thing to think about is maybe what sort of things might be producing neutrinos in the first place. And in this case, if you're familiar with gravitational waves, you'll know that there are a couple of different sources of gravitational waves that are very well understood, but they're very difficult to look for. With neutrinos, it's pretty much the opposite. So there are so many different populations that have been proposed as possible neutrino sources. And in general, you're always going to be able to find some because telescopes these days are so good that there is no shortage of astrophysical objects within even a few square degrees of sky. But there are a few different types of populations which are considered most promising, and ones that would have an optical counterpart that would be time varying. So if you're running a real-time program looking for sources of neutrinos based on the fact that a neutrino is just detected, you point your telescope and look to see if there's any transient signatures. The things that you might be interested in are gamma ray bursts. So these are relativistic jets launched by either binary neutron star mergers or the collapse of massive stars. You can also look for supernovae that have choke jets. So when a star collapses and it would try to launch a relativistic jet, but somehow this gets choked and it doesn't escape all the way. In this case, the photons would all be trapped, but the neutrinos would escape. You can also have supernovae which have circumstellar material. So these typically manifest as having these spectroscopic signatures known as type 2N supernovae. They have narrow lines from the interaction of the ejector with the CSM. And these are thought to be good neutrino sources. And then you also have on the lower row, the sort of variety of interesting things that supermassive black holes can do. So supermassive black holes that launch relativistic jets are called blazars, and even those that do not launch relativistic jets are called active galactic nuclei. Both of these are thought to be promising sources of neutrinos and also tidal disruption events. So these are kind of the big five that we look for in any kind of optical UV IR follow-up program. And the thing is that all of these will have associated timescales for the neutrino emission. So it's not enough to just find one of these, but you still have to find one of these at the right phase for it to be plausible that the neutrino could have been produced. So that's the basic idea. How would you actually go about finding one of these? Well, with the ZTF neutrino follow-up program, this is kind of an illustration of what we do. So we have ZTF, which sits there in Palomar in California, taking pictures of the sky. And it will detect on a typical night about 500,000 objects and survey roughly half of the accessible northern sky. And if a neutrino is detected by IceCube and reported, we also have information about the arrival direction, which will be a few square degrees, and the arrival time. And what we would do with ZTF is we would take dedicated target of opportunity observations. So what that means is we'll take ZTF, we'll specifically go and point in the direction of the neutrino. So the neutrino will easily be covered by one ZTF pointing in almost all cases. So we'll go and we'll take deep 300-second exposures to measure exactly what was in the field of the neutrino very shortly after the neutrino was detected. And then these two sets of information, the neutrino information and the ZTF information, we combine them in our neutrino follow-up program pipeline, which is illustrated here by a black box. And at the end, we hope to find an optical counterpart. And of course, the black box makes it very mysterious, but I hope that you will believe me when I say it's not as complicated as it looks, because actually, like most things in astronomy, if you take the trouble of explaining what you're doing, you work out that it's not very fancy at all. So if you reject stars and asteroids and things in the minor planet catalog and so on, so you reject things that are moving, also satellites, etc. And then you only look at things which are spatially and temporally coincident with the neutrino. So you only look for things within these few square degrees rather than the 20,000 square degrees of northern sky. You're usually only left with a handful of objects remaining. And of these, you can spectroscopically classify them so that you can work out what they actually are. So we have a variety of dedicated programs to identify candidates. So once we've identified a candidate, to get a spectrum and figure out what that thing is to enable us to work out if it could be a neutrino counterpart or not. And at the end, yeah, you hope to find a neutrino counterpart. And if you think I've done a good job of explaining that this is actually not a very complicated process, that's good, because the main notebook sort of homework session today for the component of this talk will be to build your own neutrino pipeline. And I hope you'll see that actually, once you get a handle on how to process alerts, just as Igor was mentioning as well, it's a very widely used and important skill. And once you get that down, you can do a lot of tasks like this with relative ease. So I hope that you'll get a better insight into how this works later today. So just to give you an idea of some statistics, we generally observe maybe 1 in 3 neutrinos. So sometimes IceCube retracts the neutrinos, sometimes they're poorly localized. About a third of the time, they're too close to the sun for us to observe. And in general, IceCube puts out a neutrino alert on average once every 2 weeks, maybe. And so ZTF does a neutrino follow-up campaign once every 5 weeks. So this plot on the right, the histogram, is sort of embarrassingly out of date. It's two years out of date now, but the rate continues, the statistics grow. We have more than maybe 35 neutrino follow-up campaigns done so far. So the numbers keep growing, and in general, what you need to do is just keep going and try and get high statistics to make statistically significant samples about where your neutrinos may or may not be coming from. And okay, I think the important question that maybe is still remaining is, what did we find with this sort of program? And so just to cut to the chase with the ZTF program, we found a tidal disruption event coincident with a high energy neutrino. So this was the first big result of our ZTF specific program. So just to give you an idea of what actually is a tidal disruption event, if you start on the panel on the left, what we know is that at the center of most, if not all, galaxies, there is a giant supermassive black hole. And occasionally, a star will be unlucky enough to approach that black hole on something like a parabolic orbit. And you may have learned even in high school that the force of gravity scales as 1/r². And what that means is that the front of the star will be pulled a little bit more strongly than the back of the star. So the star will be experiencing this net tidal force. It will be stretched. And the closer the star gets to the black hole, the more extreme this tidal force becomes. And at some point, the tidal force will exceed the self-gravity that was holding the star together. And at that point, the star will disintegrate, and we'll say the star has been tidally disrupted, and you have a tidal disruption event. So at that point, you've just shredded a star. There is an enormous amount of stellar debris. Much of it is still gravitationally bound to the black hole. So what we think happens is that maybe this debris will gradually circularize and form an accretion disk. in any case, you will have a lot of collisions, you'll have a lot of heat and light. This thing will be very bright, and you can detect it at, for example, optical and UV wavelengths with your favorite telescope. And so this is how we actually know that tidal disruption events exist at all, is because they produce this very characteristic luminous electromagnetic flare. And that's what we measure with ZTF and with many other surveys as well. So actually, the story is not just that we found one tidal disruption event, but on two separate occasions, we found probable neutrino TDEs. So we found TDEs within the relatively small localizations of high energy neutrinos. Both of them were kind of atypically bright. Actually, they were highly luminous TDEs. And so the first thing you do if you're interested in neutrino astronomy is you have to think like a particle physicist. So you never just say, oh, I found something, so it's discovery. You're always concerned with the probability of a chance coincidence. So you always have to quantify the statistical significance of your associations that you may find. And in this case, when we do the calculation, we say, how likely is it that you would point randomly at the sky and find two different TDEs by chance? And what we find is the probability is just 0.034%, or this is equivalent to 3.4 sigma, if you prefer your probabilities in sigma. So what that tells you is that it's not a 5 sigma result, but it is unlikely to be by accident that you would find two TDEs by chance. And so this is providing you with some evidence to suggest that at least some of the neutrinos that are measured by IceCube come from TDEs, and therefore the TDEs are cosmic accelerator sites. The other thing is, of course, okay, you can always have an association, you can always put a number on it, but that doesn't tell you whether or not the association makes physical sense. So I think this is where your sort of Bayesian priors should enter the analysis, and you should think carefully about whether the particular characteristics of the population and the sources you found make sense. And in this case, there is actually quite an extensive number of works considering the theoretical modeling of tidal disruption events in general and whether they could produce neutrinos or not. And in general, based particularly on these two sources and the observations of them, it's concluded that it's at least plausible. So that's kind of where we are with ZTF now, is to say that there's some evidence that it's not 5 sigma, and the theoretical modeling also suggests the story would make sense that these things could have conditions which would produce neutrinos. Neutrino astronomy is very difficult as a field with the statistics and so on, the characteristics of the detectors. So there's so far no 5 sigma sources of neutrinos at all. You may have seen in the news recently, just a couple of weeks ago, that IceCube put out 4.5 sigma evidence to suggest that the galactic plane is another source of neutrinos. But again, this is kind of the regime we're in, is that we're not 100% confident of anything yet. And I think that's maybe what makes this field so exciting right now. So, okay, I've been talking for a long time at you, so I think I'm going to sum up now. Neutrinos are a type of fundamental particle, and they're very difficult to detect, which is kind of a double-edged sword, because that means they're very good at escaping astrophysical environments, but they're very difficult for us to actually find with a neutrino telescope, because they just don't interact very much. And neutrinos are important because they can help us identify cosmic accelerators. IceCube is the world's largest neutrino observatory. It detects dozens of astrophysical neutrinos every year. Most of the neutrinos it detects are not atmospheric. Most of the neutrinos it detects are atmospheric, not astrophysical, but a small number, maybe dozens a year, are astrophysical. And we try and identify these astrophysical neutrinos and work out where they're coming from. And you can do that. One way you can do that is with a follow-up program with the telescope like ZTF. And with our ZTF program, we found 2 probable TDE neutrino associations. So yeah, I think that's pretty much it. Thank you very much for your attention. Are there any questions online or in person in the room?
Excuse me. I have a question. In the slide of counterparts of neutrino event,
This one?
Yes. You mentioned type 2n supernovae, so I come up with 5 questions. How about the 1BN or 1CN supernovae, which is also interacting with CSM around supernovae?
Yeah, so that's a very good question, actually. I think most of the theoretical modeling has specifically considered type 2n, but in principle, any supernova with interaction is a candidate for neutrino production. So I'm not sure if it would be exactly the same level, but I think in general, if you found a 1BN or a 1CN, you would also have to take that very seriously as a possible neutrino source. I mean, I have to say, like, this illustration is maybe 5 years old. Like 1CN supernova were not even known at that time. But yeah, I agree. It's actually it's more complicated than just this picture illustrates.
Okay, thank you. They are one of the main target of my survey, so I'm interested. Thank you very much.
Thanks. Any other questions? Yeah, do you want to just go ahead and unmute if you have a question? Maybe I see someone raise their hand.
Hi, thank you for the nice talk. So I have just maybe a basic question. How will you, when you detect the neutrinos from the ice cube or like the ZTF, especially for the ice cube, if you work on that, so how you differentiate the neutrinos are coming from a galactic plane or from any of these sources that are presented in this slide? So
yeah, so that's a good question. The answer is a little unsatisfying, that you cannot, for one neutrino, you can never be sure where it comes from. You can't be sure if it's atmospheric, if it's astrophysical, what type of astrophysical source it had. So what you have to do is you have to use the available information, and you just do a sort of statistical analysis to find the sort of balance of probabilities. So if you detect neutrinos, in general, you have a kind of localization like this. You have an idea where the neutrino came from. So if the neutrino is not pointed at the galactic plane, it's less likely to come from the galactic plane. The galactic plane result is actually very new, but I imagine that maybe in future, people might try and update the IceCube algorithms to try and disaggregate probable galactic neutrinos from extragalactic neutrinos. But right now, yeah, you can do it based on position. And then again, you just make a statistical statement. So you just say this sample of neutrinos is correlated with TDEs with this level of significance, and then maybe it's correlated with supernova with a different level of significance. And obviously, every individual neutrino can only come from one source, but you'll only be able to say in a probabilistic way, you'll be able to say it's more likely that this neutrino came from this source or that source, but you can't be 100% sure. The other thing is that eventually with high statistics, the energy of the neutrinos can maybe give you an indication, because, okay, so I showed that this is the kind of expected astrophysical neutrino flux, but the actual sources of neutrinos, this is a composite of many different individual sources, which will sum up. And so it's possible, for example, that the neutrino spectrum from the galactic plane and one from, for example, a blazar or a TDE, they might look different. And so again, then if you look at the energy of the neutrino, you could say this one is maybe more likely to be from one source or the other. Does that answer your question?
Yes. Thank you very much. Yes.
Thanks. Okay, and then I'm seeing a couple of questions in the chat. There's 3, so maybe I'll just read these ones out and then answer them. So firstly is, do you know the neutrino flux of a binary neutron star merger relative to supernova? I'm working on lethal transients and know a sufficient flux can cook life of Earth. So that sounds like a really cool topic. Be very interested in seeing more about that. Specifically, the flux of a binary neutron star merger. Okay, so I mean, off the top of my head, no, I don't know the exact number. However, I would say probably nobody knows the exact number because it's never been measured. There are a variety of different models which have different levels of predictions, but these models always have very large uncertainties, like orders of magnitude in the exact flux. In general, I would say that it is not so high, given that binary neutron star mergers generally take place much further away than the nearest, the nearest binary neutron star merger we had that we detected was like 40 megaparsecs, and the nearest supernova we've had is ones within our own galaxy and within all of the very close neighboring galaxies. So I'd say that like the flux in general, I would expect would probably be lower, but it depends. You have to just ask your favorite theorist for that question. Then Vishal is asking, would radio detectors in ice looking for the Ascarian radiation instead of Cherenkov light help improve the volume of observatory and help us detect more neutrinos? So that is a great question. I wonder if you have maybe seen a talk or are working on this radio detection of neutrinos. But the basic idea is that you can see in this plot right here, when you get to, let's say, this highest energy bin, right? This is maybe 10 to the, like halfway, maybe it's like 5 PeV, something like that. So that's the highest energy neutrino the IceCube would have detected in this data set, and you expect 1 a year. So it's a super low rate, and it's very difficult to do anything with. And you can imagine that this red line will extend further and further to higher energies. We're not sure, but we think it probably does. So the only way to measure something like that is to do exactly what the cosmic ray detectors did. You just get bigger and bigger and bigger to measure neutrinos at higher energy, which have lower flux values. And this is something that becomes prohibitively expensive because IceCube is 1 cubic kilometer and it costs like, I don't know, $300 million. So if you just want to make it 10 times the size directly and you kept exactly the same characteristics, it would be like 3 billion. And if you want to make it 100 times bigger, it would be 30 billion. And at some point, the NSF must say, no, this is too expensive. This doesn't make sense. However, there are other techniques to detect neutrinos, and in particular, at very high energies, so maybe 2 orders of magnitude higher, you can detect neutrinos via the Ascarian effect. So if they create air showers, you can measure, sorry, not air showers, sorry. If they're traveling through the ice, you can detect the Ascarian effect. And this basically produces a measurable radio signal. And it's difficult to detect with just one, but you can do it even with a single radio station. And the cool thing is that when neutrinos are emitting in radio is super cheap. So you can have like one antenna do maybe like a sort of square kilometer, and then you just have like 1,000 of these or 100 or some very large number. And then it's a very cheap way of creating an enormous detector volume. So I think that is the future. They're currently building the Radio Neutrino Observatory in Greenland, or have built now. And the IceCube upgrade the upgrade to IceCube Gen 2 is planned to have a radio component to measure this and get higher detector volume at high energies. Okay, then I see Bhavnesh asked, why don't we consider escaping neutrinos during the cooling period of the neutron star? I'm not sure exactly what you mean. If you mean like, why don't theorists consider it, or why don't observers look for this? But I think you always just have to bear in mind the energy of neutrinos being created. So when you think about famous neutrino, a request. Sorry, yeah, okay. So while we don't consider escaping neutrinos, so the most famous neutrino discovery was the detection of neutrinos from a galactic supernovae. And these were at MeV energies. So this is like way off to the left of my plot that you can't even see it on the axis. So I'm not sure if neutron stars are predicted to produce neutrinos at hundreds of TeV. I think the answer is no, but you should probably look that up to confirm. And then, okay, there was a request to have the lecture slides uploaded on the Slack. I'm happy to do that as well. I'm happy to share them with Michael. Were there any other questions anyone had online on questions in the room, in the chat, anything? Okay. I'm not hearing anything. Michael, is there anything else in the room, or
Anything from the room? I think folks are probably hungry, I think is what's really happening.
Yeah.
Let's thank Robert again. Yeah. Okay, so just so everyone understands, so logistically, what's going to happen now? We're going to break for lunch. We'll return kind of for the async part around 2. We have notebooks that have been developed by both Igor and Robert related to their talks. You know, finding fast transients, finding neutrino sources, all the good stuff. In the GitHub, we'll work together on those. But otherwise, thanks everyone for joining our day 1 sync section, and see most of you here in a few hours and see some of you otherwise tomorrow. Thanks.